Firstly, what causes wave energy? The winds create waves on the surface of the ocean by transferring some of their energy to the water through friction between the air molecules and the water molecule. This energy is harnessed by what is known as a wave energy converter or WEC. The WEC can be classified as one of three types, namely point absorbers, terminators, or attenuators. This piece was centered on the Ocean Energy Buoy, a variation of the backward bend duct buoy or BBDB, which falls into the attenuator category. Attenuators are characterized by their principal axis lying parallel to the predominant wave direction. Another important device is the oscillating water column or OWC, which operates by using a large volume of moving water as a piston in a cylinder, and so air is forced out of the column as the wave rises, and fresh air is drawn in as the wave falls through a turbine. At the outset of this project, there were engineering challenges faced, such as limited access for troubleshooting and potential loss of data, both due to the location of the device at sea. In order to address these issues, a design philosophy was drafted which emphasized 1. Robustness to allow for the most economic model to be constructed due to the poor tolerance of the device to various overload. 2. Maintainability, which incorporated software programming to cater for failure or erroneous condition, as well as modular design to allow for easy replacement of components. 3. Usability, aimed at minimizing operator errors during human-device interaction, combining electrical connector series and reverse polarity protection. 4. Environmental suitability, to protect the device from water ingress and inherent electromagnetic interference, EMI. Last but not least, 5. Safety, taking into account dangerous energy levels when designing the device. A major component of the Ocean Energy Buoy is the Power Takeoff System, or PTO, which is responsible for the conversion of pneumatic to electrical energy and the subsequent distribution of the latter. The PTO consists of a turbine and turbine duct, an electrical power source, electrical machine, and a load as well as the power electronic system. A Wells turbine was chosen due to its ability to produce unidirectional mechanical torque in the presence of a bidirectional airflow. The electrical machine was the brushed permanent magnet DC machine, characterized by its machine constant, armature resistance, and inductance. Additionally, a bank of 7 lead-acid batteries, each rated at 12 volts, was chosen as the power source. Furthermore, a resistor bank containing a combination of planar resistors, heat sinks, and cooling fans was implemented as the electrical load. The power electronic system operates under two modes, namely motoring and generating. In motoring mode, it is required to accelerate the motor, shaft, and turbine from rest to a predetermined speed. On the other hand, when in generating mode, it is responsible for maintaining constant shaft speed by applying a counter torque to the turbine shaft via the electrical machine. Motoring mode utilizes four major components. 1. A buck-type converter, which is used to step down the battery voltage to the required machine voltage. 2. The freewheel diode, used to protect the device from voltage spike when the supply voltage changes sharply. 3. The insulated gate bipolar transistor, IGBT, which is used for fast twitching. And 4. The decoupling capacitor, used to decouple one circuit from another and also to reduce the transmission of noise. Generating mode comprises of a power electronic converter as well as a substantial capacitor. Many sensors are installed in order to provide necessary control loop input as well as to monitor performance data such as electric machine voltage and current, in addition to temperatures of key components among others. The reflective laser sensor is one of the critical sensors aimed at measuring the turbine shaft speed. This sensor was the most convenient option, although it had limitations such as the tendency to generate short output pulses under inappropriate conditions. The control system of the device is required to complete many functions, such as the analog to digital conversion of sensor data and the provision of diagnostic output in case of error. A programmable logic controller (PLC) was chosen as opposed to a microcontroller based device due to its more suitable programming environment for field support personnel. For machine control, a cascade control loop structure comprising of an outer PI speed control loop and an inner PI current control loop was installed. Cascade control allowed the system to be more responsive to disturbances. The results of the project showed that although there were no initial errors in the PTO, difficulties arose due to failures in telemetry. Upon further analysis, some of the following observations were deduced. 1. The device tends to remain in standby for wave heights far below 0.7 meters. 2. There was a high peak to mean power output ratio of typically 4 to 1 or 5 to 1. Once the input wave power drops below the level required to maintain the system at the desired rotational speed, the turbine generator decelerates due to frictional and windage losses in the system. And 4. At lower rotational speeds, the aerodynamic stall characteristic of the turbine significantly reduces the output power capability at high mean pneumatic power levels, while at low mean pneumatic power inputs, lower turbine speed enhances the power output. Thank you for watching.